This conference will now be recorded.
All right, this is the Math 11 follow-up video for some more variety of problems from section 2.8, the section on related rates. So we're looking at example 2. It says if the radius of an oil spill in a circular pattern, so we're going to be dealing with a circle, increases at a constant rate of 1 meter per second. So that's the change in the radius. How fast is the area of the spill increasing? So what is the area's change over time? When the radius is at a specific value of 30 meters. So the first thing we want to do is write the formula, or you can even draw just a picture. Here's a circle. We know that this is going to be 30 meters when we plug it in. So the formula we're looking at, since they reference area and they're referencing a circle, is going to be A equals pi r squared. Now, if we take the derivative with respect to time for this function, remember pi is a constant or a coefficient here, this would be dA dt, because derivative of a is 1 times the chain because it's not a t. And then this would be 2 comes to the front, so it's a 2 pi times r to the first times dr dt. And we do know that dr dt is 1 meter per second, and we know that in this specific scenario the radius is 30. So we should be able to plug in and find the change in the area. So dA dt is going to be 2 pi times 30 meters times 1 meter per second. So that makes this equal 60 pi, and it's going to be meter times meter over second, so meters squared per second. So 60 pi meters squared per second. All right, let's look at example 3. This is also circular because this is a stone dropped into a lake, creating a circular ripple. So imagine ripples that are getting bigger and bigger, and I can't draw circles very good, but you get the idea. And the ripples that travel outward at a speed of 60 centimeters per second. Okay, so that 60 centimeters per second is the change in the radius, because as the circles are going outwards, the thing that's changing is the radius is getting larger and larger. Find the rate at which the area of the circle is increasing. So this would be dA dt again. Area is changing over time. When we have 1 second, 3 seconds, 5 seconds, and then we want to come up with a conclusion. So let's first of all come up with the formula again that we just did a minute ago for the change in area over time. It was dA over dt equals 2 pi r dr dt. So when we want to do time equals 1 second, first of all, we need to find the radius that's appropriate for that. So if your radius is going to change based on how many seconds have passed, then 1 second times 60, because it's 60 centimeters per every second, would tell me that my radius would be 60 centimeters at that moment. So then that means that dA dt is going to be 2 times pi times 60, and that's, remember, centimeters, not meters, centimeters, and then this is also times the dr dt, which is 60 centimeters per second. So that first answer comes out as 60 times 60, which is 3,600 times 2, so that's 7,200 pi centimeters squared per second. So this is the answer to part A. Now for 3 seconds, we have to think, okay, at 3 seconds, what would the radius be? Well, it's gone 60, 60, 60, because it's going to be 3 seconds, and each time it moves out 60 centimeters. So that's going to be 180 centimeters for the radius in that scenario. So same formula, except now we have 2 pi, radius is 180 centimeters, but the change in radius over time is still 60 centimeters per second. So then this one works out to 21,600 pi centimeters squared per second. And then for this one right here, t equals 5, that is going to be 5 times 60, which is going to be 300 centimeters. That would be the radius of that circle at that point. So now we're doing dA over dt equals 2 pi times 300 centimeters times the dr dt, which is 60 centimeters per second. And for that one, I got 36,000 pi centimeters squared per second. So what we'll notice is that the only thing that's changing each time is the actual radius length. So, and it's going up by 60 each time. So this ends up having a consistent change. It's a linear change, essentially. It's just going up by 60 each time. So that is number 3. So for example 4, we're going to have to draw a picture here. It says the altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area of the triangle is increasing at a rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when the altitude is 10 and the area is 100 centimeters squared? So let's just first draw a picture of what this is even saying. And I'm drawing the best triangle I can with these pins online. But the altitude of a triangle, remember, is its height. And this is the base. So down here's the base. This is the altitude, this line in the middle. And let's write down what we know. So we know, and if we kind of call this, let's say, H for the height, and we'll call this B. Then we know a formula about area, since we are eventually talking about area, base, and height. Area of a triangle, if you know your height, is 1/2 base times height. So we know that. Okay, so let's see what else we can figure out. We know then that dH dt is changing at 1 centimeter per minute. We know that the area dA dt is changing at 2 centimeters squared per minute. And we know at a specific instant that the height is 10 centimeters and then that corresponding area was 100 centimeters squared. We could use that to find the B at that point. So let's solve that. So that would be 100 equals 1/2 B times 10. So that's 100 equals 5B. So B equals 20 centimeters at that specific scenario moment that we're at. So we still want to talk about what is the change in the rate of the base. So we're going to take that same formula and we're going to take now the derivative of this. And it's going to be with respect to time again because it's changing over time. So this would be dA dt equals, and I have to be careful here, this is a B times a H, so this is going to be a implicit derivative where we have a product rule involved. So it's going to be first times derivative of the second plus the second times the derivative of the first. And then we're going to plug in everything we know. So we know dA dt. We know that that is 2 centimeters squared per minute equals 1/2 times B is, we said 20 centimeters in this scenario. And dH dt was 1 centimeter per minute. And then plus H is 10 centimeters. And we don't know dB dt. That's what we're looking for. So let's work out this. So we have 2 centimeters squared per minute equals 1/2, because that's outside of the parentheses. 20 times 1 is just going to be 20, but it's going to be 20 centimeters squared per minute plus 10 centimeters dB dt. And then we can work that out, taking half of each of those. So that's going to be 10 and 5. We just multiply the half through. Subtract over the 10. These are like terms because they both have the same unit of measure. So that's going to give me -8 centimeters squared per minute equals 5 centimeters dB dt. And we can divide by the 5 centimeters. Now, when you think about that over here, you might want to say that I'm dividing by 5, but really the centimeters are going to end up canceling with one of the centimeters here. So one of those is going to go away. So this is going to be -8/5 centimeter per minute. So notice it is a rate of change. So that's dB dt. That's the change in the base over time. which you could also write as negative 1.6 if they allow you to use decimals. Okay, so let's talk about the next one because we've done some circles and some triangles. Let's do some other type of shape. Let's do a cylindrical tank, which is like a soup can essentially, with a radius 5 meters, and it's being filled with water at a rate of 3 meters per minute. And we want to know how fast is the height of the water increasing. So let's draw the picture. This is a cylindrical tank, so cylinder. And we know if you wanted to find the volume, because if you're filling this with water, you're dealing with volume. Volume is always the base times the height. So the base here is a circle, so that's going to be pi r squared times the height. And we do know in this scenario that the radius 5 is 5 meters. So I can go ahead and replace that. That would be 25 pi h. We could take a derivative with respect to time for this. So that would be dv dt equals 25 pi. That's a coefficient, so we don't have to worry about that. And then this would be just dh dt. And we know that the water is filling at a rate of 3 meters cubed per minute. So that's a volume. So if this is 3, and this is 25 pi dh dt, then this would be 3 over 25 pi, and this is in then meters per minute. And that would be our dh dt. Okay. And the reason that it's in meters per minute instead of meters cubed is I didn't write my units on this guy, but this was meters cubed per minute, just in case you're wondering. And when you squared the radius, that turned that into meters squared. So that cancels out and leaves you with just 1 meter. All right, we did 6 in class together, so I'm going to jump down to 7. 7 says that we have a Ferris wheel with a radius of 5 meters that is rotating at a rate of 1 revolution every 2 minutes. We'll have to talk about what that means in a minute. How fast is the rider rising when the rider is 8 meters above the ground? So let's try to draw a picture of a Ferris wheel. And remember, a Ferris wheel, the base at the bottom comes to ground level when it's at rest. So this is the ground. I'm not drawing in all like this, the architecture here, but we know that this has a radius of 5. So from the center down to the actual ground would be 5. And if the person was 8 meters above the ground, that means you have to add an extra 3 meters here. Now, draw out this so that you kind of can see the radius here. And we'd have to figure out roughly where would the person have to be. So this is where the person is. So that this is 3 meters right here, just this height, because now they have 5 plus 3. This would also be 5 because remember, this is also still the radius of the circle. So if we consider that, we've got like this little theta angle here. So we have this inside little triangle that's a right triangle. And that means that we don't know, and I'm going to highlight this so you can see it in blue maybe. We don't know this distance from the center to here. We know it's less than 5 because it's not the full radius. So we're going to call that guy x. Okay, so let's talk about a few of the things that we know in this problem. We know that the angles change because that has to do with d theta dt is changing 1 revolution in 2 minutes. Now a revolution in a circle is 2 pi because you go all the way around, and that would be over 2, and this would be radians now per minute. So that would just be pi radians per minute. So that's what this right here is describing, okay, because it's 1 full revolution, which this is a circular shape. Okay, we also know that the distance from that person is at 8. We know that from the ground up is to 8. And we can also talk about this triangle now using some sine, cosines, and tangents if we would like to. Let's just write a few facts down just so we have them. If theta is our reference angle, then the sine of theta would be 3 over 5. the cosine of theta would be x over 5. And I don't know that we'll need it, but tangent of theta would be 3 over x. Okay, so we can find x specifically if we use Pythagorean theorem. So that would be what? 25 minus 9, so that's 16. So that's going to be the square root of 16, which is 4. So I could actually replace those x's with 4 in my formula. So since it's a nice one, I went ahead and found it. Okay, so what do we know? We know that the sine of the angle, any angle, whether or not we are at this position or not, is going to always be found by doing sine theta equals the height that the person's at over 5, which this is our height right here. It's that extra height there, so from the actual 5 feet. And if we solve that for h, that would be 5 sine theta equals h. And then we could take the derivative with respect to time. So that would be 5 cosine theta d theta dt equals dh dt. So that's going to be how fast is the rider rising when the rider is 8 meters above the ground. We're finding that change in height. And if we plug in everything we know, so we know that 5 cosine of r theta, which we already found is 4/5, is equal to, and that's d theta dt, is equal to dh dt. And that gives me 5 times 4/5, and remember d theta dt was pi, equals dh dt. And so this ends up being 4 pi, and remember this is in, I believe, meters. Yes, meters per minute. So this Ferris wheel is rotating around 1 revolution every 2 minutes, and the rider is rising at 4 pi meters per minute. All right, so I still have about 3 or 4 examples left to do in 2.8. I'm going to do a part 2 video, and that will be uploaded shortly.